All right, welcome to the deep dive. When we think about really testing if an intervention works, randomized controlled trials, RCTs, they're kind of the go-to, right? The gold
Yeah,
standard.
definitely. They're what everyone aims for, generally.
But what if you can really do that? Like maybe the intervention just works better for a whole group, a community. That's where cluster randomized trials, CRCTs, come in.
Exactly. You randomize groups, not individuals.
Okay, so now picture this. Maybe rolling out something everywhere at once is just, well, too expensive. Or maybe ethically, you feel like you shouldn't keep a potentially good thing away from any group.
Yeah, that's exactly the challenge. And that's where this other design, the stepped wedge design, or SWD, is really taken off. It
Hmm?
seems like a neat solution, an alternative to the standard parallel CRCT.
A seemingly elegant one.
Right. And today, we're going to dive into that because some recent research has turned up some, well, pretty surprising things about how it's being used.
Okay, so let's get into the mechanics first. What is a step wedge designed exactly? How does it actually, look in practice?
What's interesting here is its core structure. So in an SWD, every single cluster could be a clinic, a school, whatever group starts off in the control condition. No intervention yet.
Right, everybody starts baseline.
Exactly. Then, over the course of the study, every single one of those clusters eventually transitions to receiving the intervention. But crucially, they don't switch at the same time.
Okay.
It's done by randomizing clusters to different sequences. So the intervention gets rolled out sequentially, or stepped, across the groups over time. If you plotted it out, it makes this kind of wedge shape visually.
Hence the name. Like one city gets it this month, another next month until they all have it.
Pretty much, yeah. That's a good way to think about it. And there are variations, too.
Oh, like what?
Well, mainly two types. You've got the cross-sectional SWD, where you measure different people within the clusters at each time point. And then there's the cohort SWD, where you follow the same individuals over time, measuring them repeatedly as their cluster switches from control to intervention.
Got it. So a big part of the appeal, it sounds like, is that guarantee. Everyone gets the intervention eventually. No one's permanently left in the control group.
That's definitely a major draw, especially from an ethical standpoint, or even just practically for implementation.
It feels fairer, maybe easier to get buy-in sometimes.
For sure. And that appeal seems to be driving this huge surge in its use we've seen recently.
Yeah, that really jumped out at me from the research. This review found 102 trials using SWDs, which is, wow, way up from only 37 back in a 2015 review.
It's a massive increase.
And get this, over 3/4 of these newer trials were published just since 2012, so it's really exploded in popularity.
It has. But here's where it gets a bit concerning. This rapid growth brings us to a really critical finding from the review.
Okay?
Despite how popular it is,
Yeah.
a lot of these SWD studies, well, they're using a really low number of clusters. Something like 45% had fewer than 10 clusters.
Fewer than 10, wow.
Yeah, and 64% had fewer than 20. The researchers call this perilously low.
Perilously low. Why is that such a big deal?
Well, it's a significant issue for the statistical methods typically used to analyze these designs. Things like generalized linear mixed models, GLMMs, or generalized estimating equations, GEs.
Okay, the analysis tools.
Right. These models, they kind of need a decent number of clusters to work properly, to give you reliable, unbiased estimates.
Mm-hmm.
Ideally maybe 10 for GLMMs, but GEEs can struggle with error rates even with fewer than 50 clusters sometimes.
50. And most had under 20. So does this mean a lot of these studies might be, I don't know, underpowered or even biased in their results?
That's the major concern, yes. It raises serious questions about whether the findings are truly robust.
Because there's this perception, isn't there, that SWDs are actually more powerful statistically, more efficient.
Yes. That's a common belief, but it's a bit nuanced. It can be more powerful, but often that comparison is made against a parallel CRCT that only has one measurement point, like just a before and after.
Okay, a very simple comparison.
Exactly. When both designs have multiple measurements over time, like in a cross-sectional setup, the SWD is generally only more powerful if you have a sufficient number of steps in that rollout.
So it depends. It's not automatically better.
Not automatically, no. And compounding this, the review found a pretty significant statistical gap. Only about 22% of the trials actually reported calculating their sample size correctly in a way that really accounted for the specific stepped wedge structure.
Only 22%. That seems low.
It is. And there seems to be real confusion out there, too. Methods designed for cross-sectional SWDs are sometimes mistakenly applied to cohort SWDs, which need a different approach.
So it's like using the wrong tool for the job, statistically speaking.
In a way, yes. And there's another layer. In SWDs, you have to account for the effect of time itself, right? Things might change naturally over the study period, regardless of the intervention.
Sure, secular trends.
Precisely. But adjusting for that time effect, which is necessary, can actually reduce your statistical power. And that power reduction isn't always factored into those initial sample size calculations.
Okay, so the design itself introduces complexity, and the need to adjust for time can further sap the study's ability to detect a real effect, potentially.
Exactly. Leading to potentially underpowered studies, even if they thought they calculated things correctly initially.
So bringing this all together then, what's the main takeaway here? It sounds like the stepped wedge design is really appealing logistically, ethically. It solves real-world problems for implementation.
It definitely does offer those compelling benefits.
But the statistical side, the methods needed to analyze it properly maybe haven't quite kept pace with how quickly it's being adopted.
That seems to be the crux of it.
Yeah.
The practical appeal might be outpacing the widespread understanding and correct application of the rigorous statistical methods needed.
So we need more research on the methods themselves.
Absolutely. There's a critical need for clearer guidance and more research on just how many clusters you really need for both types of SWDs, and definitely on better, more consistently applied methods for sample size estimation that truly account for all these complexities, including that time adjustment.
It really makes you think, doesn't it, about the tension between how easily we can implement a change versus how rigorously we can measure its true impact. What stands out to you about navigating that balance?